¿Qué habrá pasado? Se quedó sin internet.
Hola. We're going to get started very soon. Please return to your seats. Yes. Okay. Thank you. Thank you. So we're going to get started now. We are running a few minutes behind, but we will kind of do a quick demonstration of some GPM and SMAP data, soil moisture data. And if we need to use a few minutes of our break, we can do that. So very quickly, before we begin with the exercise, we want to go back to the Jupyter notebook. Again, this is, I will let people get settled here. Yeah, so Jupyter notebook, I spoke briefly about this before. This is a web-based platform that allows you to run code interactively without actually having to know any of the syntax. If for people who are unfamiliar, we're going to be looking at Python code today, but we also have capabilities for looking at R. We know we have some R fans in the back here later in the week. So I'm going to share my screen and just again show you how to activate that Jupyter notebook, and then we can proceed with the exercise. Okay. Hopefully you can see my Anaconda prompt. I made it bigger. Hopefully that's better for everybody. And hopefully the most recent data was able to download during Dr. Lakshmi's presentation. So if everyone has the most recent files, that's great. If there are any problems with the installation as we try to do the exercise, that's okay. We can fix it, and this will be here, and you can run through it later. I would recommend maybe sharing with a partner if need be, if there's any problems on your computer. So just showing you again, we are in my documents. I'm in the folder for our training materials here, and I'm just going to activate my environment that we created. Honda activate, typing with one hand, Plata. And you should see that environment activated. This environment is what has all the software. This has QGIS installed. This has Jupyter Notebooks installed. And you should just be able to say Jupyter. Thank you. Jupyter notebook. Okay. And this will open up a window in your browser. So I'm now going to share that window, excuse me. Share entire screen. Perfect. Okay. This is what it looks like. I'm in my browser, and you should be able to see all the files in the training repository. And then we're just going to navigate to sessions. Session 2A and precipitation analysis. Okay, here you will see data that we've uploaded. Hopefully this is, everyone is seeing this on their computers. Any problems so far? how to open the Jupyter? Yes. Let me see if I can. Okay. If there's any problems, we can try to work through it on the break, if that's okay. And we can show you what the demonstration looks like here, and we'll run all the cells, and then we can work on it on your own computers afterwards. But this is the command Jupyter Notebook. Okay. So I'm going to open the precipitation analysis notebook here. Okay, hopefully people are following. It's going to take a second to load. Should load. Okay, bear with us with any kind of technical issues here. We'll get this sorted out. Okay. Okay. Apologies, this is taking a second to load, but is everyone, any issues in the room? Okay. Let's see. It says I'm sharing. Okay. Sorry about that. It took a second to load, but this is what should be on your screen. And again, if it's any problems on your computers, we can run through this exercise interactively. And all this does is look at Python code where you can. Oh, some feedback in the room. Okay, Dr. Venkat will jump in a second, but these are interactive cells where you can run each one individually. So you'll click on the cell, you can hit run, and the Python will execute all the commands in this cell. So you don't actually have to know Python here, it'll run it for you. And so Dr. Lakshmi will kind of walk you through the script, and we can take a look at what the outputs are. And again, if there's any problems, we can troubleshoot them after.
So it's a Python code written by Bin Fang, my postdoctoral research associate, who is on Zoom. Bin, can you hear me? Ben,
Yes,
can you hear me?
Yeah. Yes, I'm here. Hello? Hello?
Yeah, you can hear me?
Yes, I can hear you.
Okay, so can you see the Python code online on the screen? it better? Hello? Hello? Okay. So the first function is you take the previous code, which Perry just hit run, takes the Python code, creates the study area. So in this case, the study area is the shape file of the La Plata River Basin. Ben, jump in anytime you want to comment or.
Okay.
And the second function, you hit run for the second function. And the second function is subsetting it, changing the format of it. And it puts it all into the proper format for this thing. Go ahead. Okay, so then we go in and try to start doing the start and the end dates, basically starting, and this is all GPM. So we're starting and we are doing a shorter string of dates, even though GPM started in 2014 because we ran out of space on the computer. So Perry only put 5 years of data. So that's the this thing. So you can go ahead. Preload variables, generate starting string between the dates. We can hit that too. You go ahead, hit start, run. And then we start because all of this, all of the GPM scripts which Ben has worked on, and this script is available to you. If you have any questions, please email me or email Ben. We can provide his email to you. So you can use this script directly for your study. You don't have to rewrite this script or launch it in Jupyter Notebooks, as Perry has so rightfully pointed out. So you don't have to know it. But the only thing you have to change is the time period which you want the data for and the shape file of your study area. So if you want to change it to go to some other place, you can do that. Okay, go ahead. So we hit 6. And then, so basically this is going through the date and time of the year. And again, we want to aggregate it to monthly. The 7th one is finds out all of the stuff for the year. Then the geolocation parameters, where we are, the lat and lon of this place. Okay, and then this one is working on soil moisture data set. Basically, the code is same for GPM and the soil moisture. So, you know, I mean, these two data sets for NASA is in the same format. So it's very simple to use the same Python code or in the same Jupyter notebook in the same fashion. Printing all the files. And another thing, this is the 1 kilometer data, and the downscale data, which is a product which we have developed in our group, will be soon available on NSIDC. So you can get it from another vendor too. Yeah. Okay, so the number 11 is reprojecting the soil moisture data for the watershed. In our case, the watershed is La Plata River Basin. And again, this is this is the shape file for the La Plata River Basin. This is actually going in and starting to plotting all the data sets. This is making the annual soil moisture maps for each month of the year. And you can see this is all the drawing codes of Python. I mean, most of you probably know this stuff anyway. And then this is how it looks like. For 2021, you can see the soil moisture in different locations of the La Plata Basin. And the color map is blue is wet and red is dry. And actually, I will talk a little bit about this in my water cycle talk Wednesday afternoon. That's tomorrow afternoon. Yeah. Okay, so not only can you make spatial maps, but you can also make time series plot, because sometimes you want to go to a location and make the time series variability of the soil moisture or the precipitation to compare with in situ data sets. And this is the time series plot. And in this case, there is the hydrograph of precipitation and the SMAP soil moisture in the red. And you can see 5 years of SMAP soil moisture with the hydrograph of precipitation. One thing you will see in my talk is that the La Plata Basin is currently experiencing a drought, but also has a big dry down from the last 5 years. The units is, okay, the units of soil moisture is always meter cube per meter cube or volumetric soil moisture. So saturated soil moisture in volumetric, it will be 0.4, 0.45, whatever. And then residual soil moisture, the air entry soil moisture is 0.02, 0.03. Thank you. Okay, so basically, this is the, is it a different one for GPM or? Oh, okay, so the same. So basically you can do the soil moisture and the GPM and any other NASA data format in the same way. You can use these codes. Bin, did I summarize it correctly?
Yes, all correct. Yes, all correct.
Thank you. So, I mean, you can use this code, run it on your thing and ask any questions you may have. Yes. Okay.
Can you hear me? Does it admit instead of shape files to use KML from Google Earth? Can you tell?
I don't. He said, can you use
KML instead of shape files for the basin divide?
I believe so. I believe so. You may have to use a separate or a different package for that Python function. I'd have to go and look at Bin's code to see exactly what he used, but it's Python, as you know, just like R, extremely adaptable. So, we will show later this afternoon, working in a Jupyter notebook with different types of data and looking at, how to use raster and shapefile vector data sets. So, yeah, it should be adaptable to your needs.
But I have to tell you, I do not know about SMAP and GPM data sets. They may be on Google Earth Engine, but our SMAP 1 kilometer data is not there on Google Earth Engine, from what I know. So, maybe using this kind of way to do it would be easier.
The watershed that I want to analyze, can I do it?
Yes, and in the Python code, you go back up there. There is the subsetting of reprojected of the shapefile. The shapefile of the watershed is the most important part. So once you have it, you can do it. Easy exercise, because this data is only for La Plata Basin. So the easy will be, can we go down to the picture? So easy it will be. So if you can say, okay, I don't want to do the whole thing. I just want to do one small watershed. Try it out and see if the picture you get corresponds to this one, correctly. So that would be the easiest test. Yes, you can do it. And again, the data which is loaded on the drive is only for La Plata Basin, because we thought it would be more beneficial as well as relevant to this community. But otherwise, all of this is global data on NSIDC or whichever server you want to go to. So.
And I'll just make a quick note. This was meant to be kind of a very brief introduction to working in Jupyter notebooks. We did upload what the expected outputs should be already. So if you go to the outputs, you can see a figure just like this for every year from 2016 to 2021. So that should already be on your computers if you've done the most recent Git pull. And then later, if you want to try to run it on your machines, you can kind of verify that it's working correctly and you can make changes. And so that's something I will be showing this afternoon is how to take some code and make some changes depending on what your needs are. So.
And also with respect to GPM and SMAP, this is the two things which BIN specializes in. So if you have any questions, please, as I said, don't hesitate to email me or BIN directly. We'll be happy to do it. And this code is already out there. So it only will require modification of the code. Instead of La Plata River Basin, if you want to do Congo River Basin in Africa, all you have to do is get the right data, go to the right place and have the right shapefile. So it's not that difficult to go from this to Congo River Basin if you want to.
Buenos días. Una consulta. Los resultados. El resultado creo que está en 1 kilómetro. Quería consultar sobre el procedimiento o si se puede reducir a hacer un down scaling sobre el resultado. ¿Se puede mejorar todavía la resolución?
Those online, I think this may be a question for Ben, is that this was made from 1 kilometer data, and you're asking if it can be downscaled to a finer resolution. Ben, if you're online, would you like to address that question?
Yeah, actually, we have another measure data set at the 400-meter resolution using Eagle Strat data. So it depends on the input data set. You can have a better resolution data set. You can downscale the spectrometer to a finer resolution.
So what we have done is we have used the VIIRS data set, the visible infrared imager, to go from 9 kilometers map to 400 meter. And we will soon have global data set at 400 meter. But the only limitation for downscaling is the resolution of the surface temperature and the vegetation index. The finer it is, the finer you can go.
Sorry if you have already said it, but I'm kind of lost here. The SMAP data, is it, where is it? Is it in the GitHub or it's retrieving it from somewhere else?
Okay, so hopefully everyone can see my screen. We are in our session 2A. This map data is in the data folder here. And so we actually have 1 kilometer monthly SMAP and I think 10 kilometer precipitation. So this is what the code is processing. It is opening up these different geotiffs, it's projecting it and doing the analysis. So I'll show you later this afternoon, how you would actually download it to your computer. This is being provided for us.
But you know what, if you have the global data, if you put the shapefile, you should be able to cut out because it's all dependent on latitude, longitude. Yeah.
And which is the revisit time of the SMAP? It's possible to have a small time scale?
The SMAP data is 6 a.m., 6 p.m. and it has global coverage every 3 days. So there is parts which miss, but in 3 days you can fill the whole globe.
Thank you.
Questions for Dr. Lakshmi or for Ben? Or in Zoom, let me check. No? Okay. Again, if there's any problems, technical problems running the script, we can talk over lunch maybe, or later in the week, again, just stressing that it's all going to be here for you to run, and the data is online. So you may need to download it, but it will be there.
Thank you very much. The code is very interesting. Just maybe for have a better understanding of the steps, maybe you could add maybe some instructions. Well, what of the code is doing? No, because we saw in the first line the general description of a specific part, but maybe you can do it. I mean, a little bit more detailed.
Yes. So, oh, go ahead.
So the question was that in this code, which is long enough to have some more comments. Yeah. Okay. We can do that. And then, I'll talk to Ben and we can add. Ben, can we add some more comments for each of these steps so that it is more apparent to the user?
Yes, sure. I can add more comments.
You change, especially in the parts that you can change. For example, the shape file. To put it, this is where do you have to change the file. This is where you have to change the years, the days, and everything.
Yeah. Ben, especially where if the people want to repurpose this code to some different area or different time period, if you could put some comments, it will not be too many. It would be helpful for these participants in this workshop.
Yeah.
Yes, and I'll get those edits. We'll upload it to the GitHub. And then the next time you do a Git pull, that updated file will be on your machine. And that's how we're making sure things are updated throughout the week. That's a great suggestion. We will have more opportunities to work with Jupyter Notebooks this afternoon. Is there a question online?
Tenemos una pregunta de parte de Norma. Si quiero analizar otra cuenca, ¿cómo debo hacer el procedimiento? Es la primera pregunta. Y tenemos una segunda pregunta una consulta. Cuando lo corremos, se guardan automáticamente las salidas. ¿Por qué no encuentro las imágenes? Solo veo las que estaban de antes. ¿No deberían actualizarse?
So we had two questions. One is, what is the procedure if you wanted to adapt the code for a different basin? Again, we will add some more annotations to the code. Again, this specific example is tailored to the La Plata currently. That's where the data that we've uploaded is from. But we can talk about, changing the, subsetting data for a smaller area. And the second question was, forgive me.
Creo que era una consulta técnica de que no se guardan automáticamente los datos. La persona no encuentra las imágenes, solo ve lo que estaban de antes y pregunta por qué no se actualizan.
Okay, so there was a technical question about why some images aren't being updated. I think we'd have to maybe follow up later with this person just to make sure. Again, we've uploaded all the expected results to the GitHub so you can see what the code should look like. And if you make any changes, those images, those maps should change. But that may be a kind of a technical problem that we can address later.
In the plot that the image, the first one, you show what happened in the black space and in the white spaces.
That means that there is no data there.
And why?
What, because maybe too much cloud cover, too much vegetation. If the SMAP cannot give you a soil moisture, then you cannot get a 1 kilometer downscale soil moisture.
So at this moment, I cannot, I cannot have data, let's say.
Yeah, I mean, it's missing data. White means missing data. It's in all satellite images.
Mhm.
White means missing data.
Okay.
I think that- Okay, I think this can, oh, we have one comment from Mayra.
Perry, I don't know if you touch on this, but just based on the questions, maybe it would be nice just to mention that the code, this is just the script and the code can be copy and paste and used somewhere else. So all these updates or changes can be made. So if you could just touch a little bit on that, that would be great.
This is a great point. So we are using Jupyter Notebook for demonstration because it is interactive. You can kind of run the cell and you actually, it doesn't require that you know a lot about each individual step. So this is one possible application. As Mayra mentioned, you can use this as a regular code script in your workflow, and that may work better for you. And so yeah, we're just kind of comparing and contrasting different ways of exploring data using these different tools.
Yeah, I think, so after lunch, I'll be giving a demonstration of soil moisture. My plan was to use the same script. And because of the questions we've just had, what I'd like to do is do this exercise live. So Sean and I are going to be doing our homework and working up a new script during lunch. And after lunch, we'll have a live demonstration of a smaller catchment and seeing how we can develop our own time series specific using this data set. So Sean, don't eat too much. We have work to do. So would that be helpful for everyone? I wanted to make sure that the next exercise builds off of this, because now that we all have this script in our Jupyter Notebook, hopefully it's running and we can all modify it together and do something. So does that sound like a good idea? Okay.
And
So now we're on the hook. We
Yeah.
need to do it.
And I will just say in the next section on Modus and looking at different, I'm going to show an example of the full process of downloading the data to your computer. I'll show changing the dates, changing the bounding box, the area you want to look at, and running through that example. So hopefully it'll start to sink in more. And if there's any questions, we can continue to build on this throughout the week.
Question.
Yesterday we saw the Google Earth engine, and today we are on Jupyter Notebooks. Are these two different approaches or two different ways of working? I'm not quite sure of the difference and why we should use one or the other. It seems to me that in what we saw yesterday, we have direct access to a lot of data sets, and maybe here you have to provide them. So maybe if you can expand on that. Thank you.
Yeah, that's a fantastic question. The question is, we have different ways of accessing data. So Sean had a great demonstration yesterday about Google Earth Engine. Distributed cloud computing uses all Google servers to process terabytes of data in a snap very quickly, contrasting with this example, which is a scripting example. So it really depends on your workflow. You may have an application or maybe a more science-forward application that you want to be very specific on, and you want to change the code yourself and run it on your own machine. And that might be a time where you would use something like a Python script itself. If you want to analyze, larger data sets over many more years, Earth Engine would be a great way to go. And I don't know if I can maybe throw it to Sean. No,
Well, let me add
Well,
to that. So the purpose with this entire week was intended to teach you how to fish rather than giving you fish. So we came prepared with several different fishing poles. Is that a good analogy? Yes. So we have Google Earth Engine, we have the Climate Engine, we have data that can be modified and downloaded using Python scripts. So the idea here is for you all to find an approach that works best for you. So we do have many examples in Google Earth Engine. We have many examples leveraging Python scripts, different ways of accessing the data. And the whole point here was just to give you several flavors of data access, where to get the data, how it can be manipulated and used for your own water management strategies.
And I want to echo on this. So for example, Landsat data, if you start downloading it from the server, it takes long time to download and process. But using it on Google Earth Engine, it is very fast. So different approaches will require different instruments. So I think that's what it is important. And also all the data are not on Google Earth Engine. So we have to remember that. So that's the important part.
¿Hay alguna otra consulta? Sí, tenemos una pregunta de parte de Germán Fortunado y nos hace una pregunta, hacemos de Jupyter y pregunta si todos estamos en la misma cuenta de Jupyter. Entonces, es decir, si cambio algo, cambio para todos.
great question. The question is, if you make changes to the Jupyter Notebook on your computer, will it change it for everyone? And the answer is no. This is a local copy on your machine. It is running in the browser window, so it looks like it's on the internet, but it is on your machine. So this is all your local. So we're going to take another very quick break because we're running a few minutes behind, and hopefully we can have more experience, more hands-on practice with a different type of data in the next session. Okay. And if there's any people in the room who are still having problems with Jupyter, raise your hand and I will try to address that. Thank you. Hola. We're going to get started. Let's see. Dr. Bolton. Hola. Okay, so we're going to get started with the next session. I know there were some problems, some with the environment. Rest assured, we will make sure that everyone is able to run the code throughout the week. If you have issues, we can talk about it at lunch or in the mornings. So like I said, we're going to do another exercise that does use Jupyter Notebooks after a short presentation. If your machine is still updating or there's any errors right now, maybe share with a partner and we can go from there. Does that sound good? Okay. So I actually changed a little bit of the focus of my talk so far based on some feedback we had prior to the workshop. So right now I'm going to be talking about more of the kind of applications side for MODIS and VIIRS. These are kind of two of the very common sensors, and we'll talk about why. And I won't be getting into much of the academic material like Sean did yesterday. This is really kind of just looking at the types of data you can use and the application areas that you may be interested in. So we have a couple interactive demonstrations, and we'll try to wrap up in time to get us to lunch, okay? And if there's any questions, raise your hand. Okay, the objectives for my session here. First, understand some of the technical capabilities of MODIS and VIIRS. These are two very complementary sensors. We're going to explore some common applications for these types of data. We're going to download the data using an interactive Python script in Jupyter Notebooks. And then we are going to be turning it over to you to change that script as we discussed in the last session. We want to make sure that you can change the dates, change the area, and see what it looks like. Okay, so MODIS, why are we talking about this specific sensor? MODIS stands for, I will say one quick note is I tried to do 3 translations of this presentation. Not everything translates perfectly, but let me know if that's helpful afterwards. MODIS stands for Moderate Resolution Imaging Spectroradiometer. So this is one of the flagship sensors for the NASA's Earth observing system. It's used very widely. I think some people here, I'm sure, raise their hands who uses MODIS data? Good number, okay. Other sessions in the workshop will probably use this as well because it's very ubiquitous. So this is a primary instrument on board 2 satellites, Terra and Aqua. They were launched in 1999 and 2002. And what's really powerful about this is that they have a 1 to 2 day revisit time. So it's very high temporal resolution. And so they cross the equator and the mid latitudes, Terra in the morning and Aqua in the evening. And so MODIS itself has 36 spectral bands. We can show what you can do with them. And it ranges in resolution. So this is a moderate resolution. It's not super fine, 250 meters at the finest, up to 5,600 meters. What is VIIRS? VIIRS stands for Visible Infrared Imaging Radiometer Suite. This is kind of designed as the follow-on to MODIS. I think MODIS originally had a 6-year mission duration, planned mission duration, but it's still actually going. but VIIRS is the next generation. And so it extends that record. So we have a longer time frame. And so this is a very powerful sensor for looking at kind of high resolution changes for the Earth's surface. You can map vegetation, looking at water, and we'll take a look at some of those options here. Like I said, this was launched in 2011, and it has many of the same comparable type of bands that you can use, but also improves on some of the resolutions. So there's an example here from Earth Observatory showing, if you were to click that link, it brings up an article showing how it improves the estimates of fire and burned areas. This is showing that example here, MODIS from Aqua on the left, and the VIIRS from the SOMI MPP satellite on the right. So this is just estimating or looking at the progression of a fire burned area through time. So the colors refer to the different dates, and you can see that the VIIRS has a higher resolution here. So just kind of comparing and contrasting. More important, I think, for this session is really, what products are available. And so I would encourage you to go to this link in your presentations. This is the data product table for MODIS, and it'll bring up a page that is hosted on at NASA Goddard. And so I'll show what that looks like here, and you can kind of explore the different areas, application areas that MODIS can help to inform. So we have land surface temperature, emissivity, evapotranspiration, thermal anomalies, vegetation, of course. People are familiar maybe with NDVI, Normalized Vegetation Difference Index, which Sean touched on yesterday. So there's a lot you can do with MODIS, and I'll just show you one of them. So again, we're just kind of looking at the thermal anomalies / fire data set. Again, this was changed slightly from my original topic because we understood that there was interest from some of the member countries on looking at hotspots and potentially fires. So when you click on this product in that website table, you'll see the full product name here, as well as the short name. This is kind of the code for that specific product, and that's important. We'll be looking at that later in our Jupyter Notebook script. So to visualize the data, again, this is keeping in the fire theme. I'll play this video from the Goddard's Scientific Visualization Studio. And this is VIIRS fire and fire thermal anomalies through time in a time series. And you can kind of see how these different events change throughout time and ebb and flow. So this is something that you can do. It can be very powerful. So what makes, why are we talking about this product? Why is it maybe of interest to you? And I would really note, Sean touched on this yesterday in a very helpful way. Satellite information, it's always about trade-offs, right? This is a moderate spatial resolution. It's not going to be as fine. MODIS cannot, for instance, penetrate cloud cover. So for certain applications, it may be limited, but what it's really good at is it's fast. So at mid latitudes, we can image the Earth's surface. It images a spot on the Earth's surface up to twice a day. And so this is what we call near real time. The definition that NASA provides for near real time is simply that standard products are available within a couple days. Near real time can be within a couple hours of that satellite overpass. So for things like disaster response, flood mapping, things where you want to be able to image the surface very quickly, it can be very helpful. And that goes for fires as well. So NASA has a platform for looking at kind of near real-time data. I'm providing the link here. This is, it's called LANCE, NASA's Land Atmosphere Near Real-Time Capability for Earth Observing Systems. And so Again, I talked about a couple examples here. They have a near real-time global flood product. This is something that John Bolton's lab has done in the past, looking in the lower Mekong River Basin. So again, twice a day, you can produce a flood map here. So this is showing the red pixels are areas where MODIS has identified surface water, and you can kind of quantify that extent. And this is actually something our very own John Islander will be kind of elaborating on later, how to use MODIS to quantify aerial extent of water. We also have, again, getting back to fires, there's a specific dedicated platform for looking at fires. It is called FIRMS, the Fire Information for Resource Management. And so I can bring that up here. They have this will load. They have a global mapper where you can kind of visualize the current fires based on the different satellite observations here. And so let me see. One of the things I had planned, if we have time, is to show how you would actually take this FIRMS data, this fire near real-time data, and bring it into something like QGIS. So if we have time for that, is that something to be interested to people here? Yeah, okay. So let's see, let me go back to the presentation. Oops. So let's try to work through this. I'm going to try it out. I know there's been some hiccups a little bit with the installations, but for the people in the room, was everyone able to install QGIS correctly? Some nods, see? Okay. So I have kind of two exercises here that we want to try to make time for. One is we're going to import FIRMS VIIRS data into QGIS to visualize it, okay? So the first thing you need to do, does everyone have this presentation open on their machines is my first question. Yeah, okay. So the first thing you'll need to do is go to, to this first link. You need to generate a map key. This is a free step. You'll have to type in your email, and I can show you what that looks like here. Oops. So it should take you to this page. And again, if you don't want to do this right now, I can show you what it looks like. And so what we're showing here is different map layers that QGIS can import natively and visualize in real time. So I'm just going to, there's actually a tutorial here. Let's see. Tutorial and examples, QGIS. This is also linked in the presentation showing you the different steps, but I'm just going to demonstrate it on my machine. And if there's any questions later, we can work through that. So you can see my map. Okay. So this is our map file that everyone should have if you've downloaded and done the Conda installation. And all I'm going to do is decide which fire layer I want to ingest here. So I'm going to do the VIIRS 7-day fires. I want to copy this link. One second. And then in QGIS, I'll go to layer. Data source manager and create a new layer. So this will be, I'm going to call it FIRMS. And I'm going to paste that URL. Okay. So this is all in the tutorial. This is just showing kind of something you can do very, very quickly to analyze and visualize something like MODIS or VIIRS. And you'll notice in this URL that I've included here, it's going to ask for your map key. So when you do sign up for that, it'll send you an email, and all you do is insert your own key into that URL. So I'm going to do that right now. Okay. Oops. Okay, so again, we're running a little short on time, so the steps we can talk about later, but what I've done is I've taken that data that Lance hosts in near real time, it's updated frequently to the internet, and I've connected it just right to QGIS. And I'm just going to pick one of these layers. You can see the title, 7-day fires and hotspots, as well as a description about what that entails. And I'm just going to click it and add to map. And it might take a second to load. Okay. So this is looking at VIIRS detected fire and hotspots over the last 7 days. And this is a global product. We're uploading it or doing it right from the internet, and we're visualizing it here. And so this is something that you can kind of do if this is of interest to you. It's a couple steps. And any questions so far on this? Questions? Okay. Too fast, you're saying? Yeah, so I wanted to kind of do a very quick overview of this part, so we can spend more time on the Jupyter Notebook, because that is where you'll be actually downloading MODIS data using Python and changing the parameters yourself. And so that exercise I think will be helpful, and we'll have some time to talk about different products that you may be more interested in. So let's look at that now. Oh, yes, question here.
In the URL, where do you put the key?
Mhm.
Can you go back to the?
Yep. So layer, data source manager. So when you create a new web map layer, you paste the URL here. So I'll show you. So these are the different products here. 24 hours fires, 48-hour fires, 7-day fires. So I'm going to copy that link. That's what I put in the URL. And then your map key is where you insert your map key. Okay. So the question we had was how to actually get the map key. There is a link in the PowerPoint that links to the tutorial, and it'll bring up this website and map key here. So you can request a free map key. All you do is type in your email address, and it'll send that to you. Okay.
The link to the web is on the presentation.
All the links are in the presentation. I just brought it up in my browser to have it preloaded.
Okay, thank you.
Okay. So that was a very quick exercise. I know it went a little fast, but I wanted to make sure we have a little less than an hour left for the next exercise before lunch. So this is again, the second exercise here. Is everyone ready to move on? I should ask. See some questions? Yes? Okay. We're going to move on to our second exercise. And this is where we'll be doing another Jupyter notebook to download MODIS data, to analyze NDVI, and to plot the maps. And then we'll kind of talk about how you would change that script for different types of applications. If you want to look at flood maps or thermal ranges, things like that. Okay, so I'm going to pause here for 1 second. Any questions? Okay. The first thing you need to do for this exercise, and I'll say that the example I'm going to show is already preloaded, so we can run through it together. If you want to do it yourself, you will first need to sign up for a Earth Data account. Okay. This is a platform that helps to manage Earth science data through NASA. Other presentations later in the week will be using our Earth Data account, so it's a very useful thing to have, and it's very simple to get. So you kind of click on this link. Oh, well, I already have an account, but you can type in your email and sign up for your own email and password, okay? So are people ready to move on to Jupyter Notebook? Yep. Okay. So again, we're going to open our Anaconda prompt. We are in our repository here with all our files. And if I'm going too fast, raise your hand, please, and I can slow down. And I'll type in Jupyter Notebook. Okay. I'm just going to navigate to our session 2A, MODIS access and analysis. Again, we have our data folder. I have data on my machine that's already downloaded. On your machine, it's not downloaded. So I'll show you how to download it to your own machine. And it also does not have the outputs here. So we're all going to do this in real time. So this is our Jupyter notebook for the MODIS exercise. You should be able to click it. Okay. Are people following along? See? Okay. So Juan Carlos had a great comment in the previous session. I tried to do a good job of annotating my code because I knew that some people may not be familiar with Python or the syntax of these programming languages in general. So I tried to show what each kind of step does here. So first thing I'm going to do is import all our packages. The first parts are just Python packages that are used for manipulating geospatial data. But down here, you'll see specific packages for MODIS. So Python is a language you can create any package you want, and some people have made a super helpful package just for MODIS data. It makes it extremely easy, and we'll show. So this should be installed on your environment already. If there's any problems, again, we can talk about it. So I'm going to run this cell, and you'll see a little asterisk here. This means it's thinking. Okay, this little warning, that's okay. So the first thing we need to do is we're going to authenticate our session. This is where when you sign up for the Earth Data account, you'll change these lines here in cell 2. You'll insert your username, you'll insert your password. Okay. I didn't show you mine because it's my password and it's private. And this is just an example here, but Ibrahim later in the week will show a similar code. There are ways to have your passwords securely on your computer without actually putting it in the script itself. But for this time, we're going to enter our username and password, and then we're going to create a session to communicate with NASA to get the MODIS data. Okay, so now we are creating our command. We're going to say, what product do we want? Okay, so some of this isn't that important in cell 3 for the people listening on the web. But right here, you'll see the short name, which is early in the presentation. So this is a specific product. This is the code for this product, mod 13A1. This is a 16-day vegetation index. So at the end of this exercise, I'm going to ask you guys to maybe change this to something else, right? Whatever you're interested in looking at. If you want to look at fires or thermal emissivity, if you want to look at water, you can change that here. We're also going to set up the parameters for our data download. And I have a note. MODIS files can be large, around 50 megabytes or so. So just be careful as we scroll down. Here's where we have our target dates. Okay. I'm looking at 2 weeks of MODIS data. You can change these dates as well. But if you make it 2 years, you'll be downloading a lot of data to your computer. So be careful. So I'll run this cell here. And you'll also notice, Granule client is not, I got an error for an import, but we can come back to that later. My example is already loaded up here, but you also notice I've included the shapefile for the La Plata River Basin, and I've printed the bounding box. So this is the 4 corners of that basin. So if you wanted to look at a different part of the world, these are the coordinates for La Plata. You can change that bounding box to your own area. So that's important to note. Okay. Is everyone following along so far? Yeah, okay. The next step, cell 5, this is where we actually download it. I'm not going to run this right now. I've already downloaded it to my machine because it does take a little while. Like I said, these are fairly big files. But you can see it's going to send that command up to NASA. It's going to say, it's going to check which MODIS files are available for my date range for that shapefile. And it's going to download those into your data folder. So I'm just going to show you here. Okay, so that's what it looked like. So when you run this in your machine, it's not currently on, but you should see that kind of start to download the file. It may take a little while. So this is what the MODIS files look like. These are on HDF format. So, okay. So we have our period are now downloaded to our data folder. So let's start working with them. We're just going to do a few commands here to process the data. Again, this exercise is looking at NDVI. This is Sean talked about this yesterday. Excuse me. This is a vegetation index that uses the specific relationship with lush green vegetation and how it interacts with infrared and red radiation. So I'm just gonna run through this here. All I'm doing is saying, let me see if I make this a little bit bigger, actually. Is that better? We're saying, let's go to the data folder and let's find all files that have this HDF suffix on it. And then we're printing. So right now I've downloaded 9 files for this specific region. Now we're going to manipulate it. So we're going to use some of those packages we imported in the beginning. These are just geospatial manipulation packages. And we're printing, just an example, we're going to print the different bands in just one of the files. Okay, so this is what prints out. Little hard to see. And you can see within this one MODIS file, we have multiple different bands available. So we have our NDVI here, 16-day NDVI. We have enhanced vegetation index, red, near infrared bands. So these are things that you can manipulate based on your interests. I'm just going to show you how we would pull out the NDVI specifically. Okay. So we're going to extract 16-day NDVI band from our MODIS files. There's a few commands here. Like I said, I did try to annotate what each step does for those not familiar with Python. We're kind of creating an empty list, and then we're looping through each file, each of the 9 files. We're going to open the files. We're going to mask it if need be, and then return it to a single list. So this may take a second or so. Again, you can see, okay. This is what prints out. And basically we're just saying, here's our dimensions of our final data set. MODIS 16-day NDVI from the Terra satellite. Okay. Now we're just going to plot it. So this is just an example. We downloaded it to our machine. We've done a little bit of processing in a few lines. We're going to plot just the first one to see what it looks like. Okay, this is what pops up. Are people following along on their own machines? Yeah, perfect. Okay, love to hear it. And you can see we've plotted a single MODIS file. We've looked at the color map here, typical NDVI, red, yellow, green. We've added a title. Okay, you can change any of this. People who have worked with NDVI may note something strange about the scale here on the right. NDVI typically is between -1 and 1, so we're just going to kind of fix that. So part 3, combining all our 9 files into a single one for the entire La Plata Basin. And we're also going to apply that scaling factor to make sure the values that we're seeing are between -1 and 1. So again, using a package to merge all of our files into a single object, I'm going to scale them correctly, and I'm going to then export that object into a GeoTIFF. So again, when you run this on your machine, you should be able to, it's going to think for a second. Depending on how fast your computer is, it may take a second. But when you go to your outputs folder, still thinking. Okay. Here we go. NDVI merged. Okay, so this is the product that appeared in real time when we did that command. Okay. We are then going to reproject it. All that means is we're just trying to get into a format that can play nice with the rest of our data. So this is using a utility called GDAL, very common geospatial utility. Someone wrote a great Python package for it, and now it's as easy as one line, right? So we're taking our merged file that we just created. We're creating a new file called NDVI warp. And to run this, Let me close my email so you guys aren't bothered by that. Okay. I'm going to run this cell. And I open up my outputs again, and now we have NDVI warp here, okay? And the last step, I believe the last step for this. So we have merged and reprojected our NDVI raster. Now the last thing we want to do is we want to clip it to the La Plata Basin and see what it looks like. So we're just going to clip it to our plot the shape. This is our shapefile. We're going to run the code. It's going to produce one more geotiff and save it to our outputs folder. And let's see if that worked. NDVI clip, right? That should look familiar. I know it's maybe a little small, hopefully for the people online, they can still see, but this is our clipped NDVI. And now we just want to plot it. We will open it up here and plot. And I'm using that same red, yellow, green. This may take a second. Everyone following along? Still thinking? Okay. Okay, here we go. So may not be perfect. It's still a pretty simple plot, but this is just, I really wanted to create a kind of very straightforward exercise showing you the whole process from top to bottom. How do you download the data? How do you manipulate it? And how do you plot it? NDVI, extremely common for looking at vegetation. MODIS is a fantastic sensor for looking at this type of data. Hopefully people can run it on the machines. I know there may be some errors we have to work out, but what I'd like to do now with our remaining time is kind of turn it over to you guys, okay? So part 4. We want you to change the script. So if you want, you can do it right in this code itself. If you want to keep this how it is, I suggest you make a copy. You can call it whatever you want. MODIS access new. And in that copy, you can open up the script. And I've given some suggestions of things to try, right? So the first thing would be, you probably want to enter your own username and password in the script once that gets all set up, right? That may take a second. But then you can also change the parameters. Okay, so I'm just going to scroll back up here. Like I said, you can change these to any dates you want, right? Right now, this is what I have. Feel free to play with that. Feel free to play with the actual data product itself. I'm using this data product, mod 13A. But if you recall from my few slides earlier, you can go to the MODIS website. The link is in my PowerPoint, and you can pick any one of these different application areas. There are snow cover, chlorophyll. Let's just take a look at snow, for instance. Okay, you would open this up. You would find your short name, and you would replace that short name in the script. And if all goes well, it should download totally new files. And when you do the plots, it'll be totally new plots, okay? Does that make sense to everybody? Okay, so we can take a few minutes. I will walk around and try to troubleshoot for parts 1 through 3, okay? And then I can move on to the end of the presentation. Does that sound good? Okay. Any issues, any questions in the room or online?
Here I put my threshold. And then here my passcode.
Un minuto. We're gonna. Hola, everyone. Okay. We're going to wrap up. I'll let people get headsets on. We're going to wrap up that session now so we can eat. But if people still have questions, Juan Carlos, I need to talk to you. Sean, I need to talk to you. We can talk over lunch as well, or throughout the week. And so that, we did have some more discussion that I had here. I'm happy to continue this discussion later to talk about, what types of products you would have used based on your specific application areas. What kind of data are you interested in? That's what we're here to find out. This is just one very simple example. I know some people, well, let me get a show of hands. Who was able to run and change the script? Okay. Anyone else? Yes? Okay. Still people having some problems. So we will work through them, but we just wanted to show you an example and provide the tools so we can build on them throughout the week here. So with that, I will end my session and we'll let everyone get some food. Thank you.
Eso para el almuerzo ya está listo, pero también nos informan que podemos hacer uso del deck por si quieren tomar aire también y tomar el lunch allá afuera.
Yeah, I'm just going to talk. About some. Hey, everyone. Hola. How was lunch? See if I can turn this on. I guess when we have questions, I'll put these on. So. Okay. It's always challenging to speak right after lunch because everyone's eyes are going like this and they're falling asleep, but that's okay. So I'm going to talk a little bit more about soil moisture. When we were designing this workshop, we were trying to find what hydrologic variables were of importance to the basins. And soil moisture and precipitation, of course, are pretty easy to identify as essential variables. So if you just walked in the room, I'm John. So I'm from NASA, but my background is on soil moisture remote sensing. I studied with Dr. Lakshmi here. And I remember when I first met him in 1998, he said, one day there will be a satellite mission devoted to soil moisture. And it turned out that in 2015, NASA launched its first mission that was dedicated to global soil moisture observations. And that is the Soil Moisture Active Passive Mission. And that's what we have here. I think this is on auto scroll. And that's what we see here. And I'll go into a little bit of detail on, I know Sean McCartney mentioned soil moisture and some theory of remote sensing. And Dr. Lakshmi also mentioned it this morning as well. But as a hydrologist and as someone who is focused on hydrologic applications, soil moisture is key. And it is the boundary condition between the land and atmosphere. We've found that the reason why NASA has a soil moisture mission is we did a big study called the Decadal Survey, and we surveyed all the US agencies, all the subject matter experts, and soil moisture came to the top tier as the essential variable for hydrologic monitoring and forecasting. And as we know in hydrology, if you have a numerical model, this is a numerical simulation of nature. You're trying to mimic nature as closely as you can. Turns out that soil moisture is a key way of doing this, of constraining that numerical model. So, no, that's not right. Yeah, so if you look at NASA's Earth fleet, we have more than 18 satellites that are dedicated to observing different components of the Earth, energy, and water cycles. And soil moisture, of course, is a key part of that. And we have a few satellites that are able to observe soil moisture. And I mentioned the Soil Moisture Active Passive Mission, or SMAP. And so I'll be focusing on that here. And Sean discussed this, but just for everyone's awareness, the reason it's called SMAP, the reason it's called active and passive. The passive part is just like our eyes are capturing ambient light. And the active element is like a radar gun for capturing speed on a highway. Both of these have advantages and disadvantages for observing soil moisture. In the electromagnetic spectrum, the microwave frequency is sensitive to soil moisture. And using a passive approach, just like our eyeballs, we have very high sensitivity to the brightness, temperature, the emissivity from the land surface that is dependent on the amount of moisture in the soil. And the active part is also sensitive to soil moisture. You have an ability to have a higher spatial resolution. However, it's also sensitive to trees and surface roughness and vegetation, essentially. So what we try to do is combine both of these in a strategic way.
Hence, we have SMAP, so the soil moisture active passive. And why this is really neat is because by leveraging the microwave frequency, specifically the L band frequency of the electromagnetic spectrum, we're able to sense through clouds, through light vegetation, roughly 5 to 10 kilograms per meter squared. That's essentially a young corn crop. We can still detect soil moisture through this. So, but the objective of doing this is not just to sense soil moisture, but it's having frequent repeat times. Our goal here is not to just have a fancy observation of the ground. It's to have something that's usable, that can be repeatable and be used in a hydrologic application for water resource management. So in order to do that, we have satellites that are placed on a specific orbit. So they are timed so they can optimize their spatial resolution and temporal resolution and the depth. So we have a great understanding that this is a key to hydrologic modeling, and it really drives a lot of processes that link the terrestrial water, energy, and carbon cycles. And if you're in the business of land surface modeling, which many of us are, we understand that having a gauge-based observation complementing a satellite-based observation can really improve your hydrologic model and reduce your uncertainty. And we like to say we drive that model towards nature. So I'm going to give just a quick run through of some of the products, and what we're going to be doing after this short presentation is that we'll go back and revisit the exercise that we did with Dr. Lakshmi, looking at GPM and SMAP soil moisture, but Perry and Sean, during lunch, instead of eating, they went and modified that exercise, and we found shape files specific for La Plata Basin, and we're going to be doing this together. So there will be a test. I lied to you earlier. There will be a test here. So we'll be able to do this live together. So let's see. I'm not going to talk about that. You don't need to know that. So the SMAP data product availability, I think mostly for this crowd, we're interested in the level 3 and level 4 products. So the level 1 are typically brightest temperatures and things. Level 3 and level 4 are products specific for applications. And the key here is the level 4 is a merged product that has been merged with the catchment land surface model to provide root zone soil moisture. So the passive microwave has its sensing depth is dependent on frequency and altitude. And also the type of soil, the amount of organic content in the soil, and the amount of water in the soil. But you can roughly say that it is on the order of 1 to 5 centimeters, depending on the type of soil you have. So how do we take that surface observation of soil moisture and make it usable and relevant to root zone soil moisture that is really needed to drive a lot of hydrologic processes? This is done through data assimilation. So data assimilation essentially is a strategic merging of two data sets. You're assimilating a data set. Every time you have an observation, you replace the modeled element with your observation. What I like to tell my grandmother about data assimilation, I said, well, you can think of data assimilation as if you're driving down the road, you're driving and you're sleepy, right? So when you're driving, you're the model, you're the land surface model. You're still going in the right direction. And when you close your eyes because you're tired, you veer away from the center line. And when you open your eyes, hopefully you correct towards the center line. That's data assimilation, essentially. So every time there's an observation, you correct towards the center path. And that's how the level 4 product is developed. So what's important for you to know, the level 3 radiometer product is provided at NASA. I'm going to provide some links here. Essentially, we have full global coverage every 2 to 3 days. That's important, number one. And the spatial resolution, the one that's probably most likely to be used here is a blended product that is provided at 9-kilometer resolution. There are also higher resolution products. Dr. Lakshmi mentioned this before, at 1-kilometer spatial resolution. They all have advantages and disadvantages, and this is for us all to explore and determine what is best for our application. There's been a lot of progress in the type of data, the format of the data. So it could be on an easy grid. This is a standard NASA format for satellite data. It can be in a gridded format as well. I just mentioned the level 4 SMAP product. So these data come, you can have actually the level 4 product is provided in daily. Here they have a version that's 3-hour time averages, but essentially it is they average to a 1 day product. I'm going to skip over that. These are all the enhanced products. Again, what I think is probably most important for this crowd is this daily soil moisture radiometer product and the surface and root zone soil moisture product, and this daily. No, forget the last one. We don't need that right now. This is what they look like. Hey, by the way, I don't want that. What should I just do? Oh, sorry, muted. Okay, cool. So this is what they look like, and you can see the difference between a coarse scale product to a SMAP Sentinel. This is combining the microwave based product with a visible infrared product to have a higher resolution, and the SMAP Sentinel Active 1 kilometer. This is similar to what Dr. Lakshmi did. In fact, this is his work. So this is just a demonstration of the different spatial resolutions over different basins. So you can see how these have been developed, and what they've done is they've tested and worked over this calibration and validation of this downscaling algorithm. I do like this video, so I'm going to show it because I made it. It's pretty cool. So what this is all this is 2 satellite observations playing at the same time. So there's no model involved. And I love this animation because what this shows is the value of having concurrent satellite observations. What you're seeing in the green and yellow, this is precipitation from the GPM mission that we discussed earlier. And it's overlaid with soil moisture anomalies. And you'll see that the soil moisture anomalies follow precipitation. It's not rocket science. It makes a lot of sense, but it's great to see here because we are able to convey this concept of precipitation memory. And it's just cool to see how the world works sometimes just using satellite observations. Yes, of course, we know that when there's rain, the soil gets wet. But it's really valuable for discussing why we do this, why we use a satellite-based observation, and why we try to complement existing ground-based observations. So this is a great teaching tool. And there's a link to this. We can provide it if you guys want to use it in your classes and for your teams. While I'm on that topic, there's a great resource. It's the NASA Science Visualization Studio, SVS. And it's a lot of cool animations, a lot of fantastic education tools for you to access. Speaking of access, this is SMAP Data Access. So again, I have the coolest job in the world because we don't have to sell anything. All the data, all the value-added tools and all the models that we are discussing are free. So we're unable to try to sell any of this stuff. So it's great. It's a great pitch. So there's a few different ways that you can access the SMAP data. the NSIDC. This is the snow and ice data center is linked here. This is one way of doing this. And they come in different formats. I'm not going to go into that because, to be honest, it's been a few years since I did that, but I think you know some of the specifics based on Sean's presentation, and we're going to discuss a format in our exercise. There's also the Earth Data Search. This is the link, and you can search based on the SMAP data, the spatial domain, and temporal search for the data that you need. There's also SMAP products at the DAX. So if you're getting an idea now, there's several different flavors of the data, different ways to access it, different ways to view it. And so what's interesting here is if you are a new user of satellite data and you're curious of how it is represented in your geographic region, you can visit the Worldview Earth data site, and you can browse the imagery and get an idea of how it looks. Okay, so this is the fun part. So my career has been mostly aligned with applications, soil moisture applications. So as I mentioned, there's a lot of different opportunities for applying soil moisture. Weather forecasting, of course, because soil moisture constrains that boundary layer between the land and atmosphere. So we have a lot of operational products and demonstrations of soil moisture applications looking at for the United States Air Force. So in fact, the branch that I am leading at NASA Goddard Space Flight Center, we are now providing a data simulation product of SMAP into the US Air Force. So this is driving US military operations strategically and improving weather forecasts. So also we have GEOS, GMAO as a SMAP observations. This is an operational, another extension of SMAP data assimilation. Several different examples. Agriculture, of course, soil moisture is used in agriculture, and we're seeing a lot of great opportunities for leveraging soil moisture, for improving crop forecasting models, for improving agricultural yield estimates, for looking at identifying areas and times of flash droughts, of agricultural droughts, and hydrologic droughts. And I'll show a couple examples here where we're working with USGS and others where we're looking and we're seeing how soil moisture alone can be an indicator and improving stream flow forecasts. So this is a pretty busy figure, but what I wanted to just show is that this big arrow is a way of demonstrating the evolution of a concept of, and initially how I mentioned the decadal survey, the need for global soil moisture observations for hydrology. This drove our mission development of the Soil Moisture Active Passive mission. And this was carried through our Science Data Processing Center, targeting specific data types and spatial and temporal resolutions, and finally driving towards hydrology applications. And at the end of the arrow, you see a hydrology application looking at the famine early warning system. This is a partnership with NASA and USAID. So this is another operational product coming out of the NASA Goddard Space Flight Center in partnership with several other agencies. This is my bread and butter. It was for many years. So this is the NASA USDA Global Land Data Assimilation System. And the big message here is that we were able to take soil moisture observations from initially it was the AMSR-E, the Advanced Microwave Scanning Radiometer, and then the European Soil Moisture Ocean Salinity Mission, and then SMAP. But we assimilated using a data or ensemble common filter approach to improve a 2-layer soil moisture model that is driving the Foreign Agricultural Services crop forecasting models. And it's great. So in my office, I have posted above my desk. I got feedback from one of the analysts, and he said, they're in the business of providing global crop forecasting estimates. And he said, oh, for the first time in 20 years, we have reliable estimates of soil moisture in Southern Africa. What's interesting about this is in areas where you have high food insecurity and water insecurity are also areas that typically lack gauge-based observation of soil moisture and precipitation. And this is where the value of satellite data is realized. So it's kind of cool. So I printed it out and it's above my desk. So this is a very new example coming out of our lab. This was produced by Tasnoom Varoof and Hung Lee, study with FinCat. And essentially what you're looking at is how we can improve agricultural forecasting in Argentina. So we're working with the Buenos Aires Grain Exchange, and we're looking at how we can forecast NDVI. And we talked about this yesterday, the normalized difference vegetation index. It's a satellite-based indicator of vegetation health based on visible and near infrared spectrum. But what we're seeing is with a lead of 1 month, we have 75% improvement over existing approaches of NDVI. Up to 3 months, and we have a 67% increase. The point here is that we've taken satellite data of soil moisture and we've applied it, and we're showing real improvement in our ability to forecast agricultural yield. And this is, I think it's a big deal. I hope it is. Okay, so I have a couple other short examples. This was provided by Joe Santinello and Patricia Parker from NASA. And we're looking at just in the United States of irrigation. And we're seeing that irrigated land is really driving mesoscale changes in weather, right? And why is this on auto advance? I don't know why. I don't talk that quickly. So what we're seeing here in this red line is an increase in irrigated acres from 1890 up to 2018. And on the right, we're seeing water use. And so this is an US irrigated acreage and water use per capita. Was it per capita? No, per acre. And we're seeing this increased need of irrigation. And how do we obtain irrigation observations? We can do this using soil moisture. So we know that when in areas that are irrigated, they have evaporative cooling, so they have a different signature in the temperature and in the thermal signature as well as soil moisture. And I lost the last 2 slides. I don't know why. Okay, we'll skip that. But I think this is my last example, maybe. But this wasn't something we did using Google Earth Engine, and I'd really like to provide the Google Earth Engine links to these scripts. I think we do have that. But what this is, oh my God, why is it doing that? What this is essentially is on the left, all these are correlation of precipitation with stream flow. And on the right is soil moisture and stream flow. And we did this with, I think, over 900 basins in the United States using Google Earth Engine. And we did this assessment, and we found that using the soil moisture was a great indicator of stream flow forecasting. And it was all done in Google Earth Engine, all using freely available data. And if you look at this publication here, SAZIB 2020, it was in water. It was pretty cool. And aside from the soil moisture business, it was a great opportunity to highlight the value of Google Earth Engine, this cloud-based data for doing spatial analysis and pulling in these data sets. So if you go to this paper, you'll see that there are examples in the Google Earth Engine for how to access the data that we use to do that. So you can reproduce this. But yeah, I think this is my last example. So of course, soil moisture must be related to fire probability in some way. So this was a very, very straightforward paper that was led by Nazmish SAZIB. And what we're looking here is the soil moisture anomalies and fire count. So the fire count is satellite-based observations of fire. And we know that soil moisture is a leading indicator of future vegetation conditions. So when there is a negative soil moisture anomaly, this is an indicator of future vegetation conditions that are ripe for fire. Again, not rocket science, but it's really cool to do to demonstrate very clearly this connection to satellite-based soil moisture and satellite-based observed fire. That was the first step. And so now the second step is saying, okay, well, let's take this satellite-based observations of soil moisture and start applying it in our fire risk and our fire warning systems. And that's exactly what we are doing. So this is the exercise that we did earlier with Dr. Lakshmi. And what we're going to do here right now is we've, based on some questions about how to change the spatial domain of the SMAP data that is provided in the Jupyter Notebooks exercise that we have. How do we apply that? How do we modify that together and change the time series of precipitation and soil moisture in the spatial domain? So was it hydrosheds? Yeah, so what we have, we're going to provide a link to a website called Hydrosheds. And what this is a way of, it provides a shapefile of a spatial domain that you select. And we're going to pull this into our Jupyter Notebooks exercise. And then we can complete this exercise together. I believe it. I believe in us. I think we can do it. Perry doesn't think so. So that's it. Okay.
Thank you, John.
Is there any questions about any of that stuff? If you want to ask questions about that? I knew that you would have a question. Yes. I didn't mention Salcom, if that's what you're asking.
No, Salcom. No, it's a question on the slide. You show the correlation with the heat signals. Next one, probably.
This one?
This one. I cannot see from here. What's the time step or the horizontal division? Is a month?
Yes. So this goes from, let's see, this is October of 2019 through, yeah, it's 2 years. Or 1 year, essentially. Okay. This is October 2019 to July of 2020 right here. So I would say June, July, October. So it's October to October.
So the anomaly of soil moisture is giving you an anticipation of roughly one month with respect to the fires.
Right. Right.
So it's a good.
Yeah, these are months.
Yeah.
Yes.
Okay.
Yeah. And so we did this, and thanks for the question. This paper was produced right after the California fires and the Australian fires. And so we thought, hey, why don't we look at the data and see what we can see? And this was done at a pretty coarse resolution at 10 or 9 kilometer resolution. And you can see here, and this figure is essentially just a time series of the soil moisture anomalies. And you see here in July of 2020, and it was a precursor to this very, very high fire count event, which correlated with the very, very low soil moisture anomaly. And it's more of a qualitative analysis of saying, look, we see a connection there. And so now we're taking this and extending it into more quantitative approaches. And we're working with in situ ground soil moisture observations. We're working with NOAA, NIDIS, a bunch of different agencies of seeing how we can strategically bring soil moisture observations from satellite into wildfire risk models.
Thank you. One more very briefly.
Sure.
For the level 4 product of SMAP, the model, is it forced with GPM or?
Ah, man, that's a good question. So that's Rolf Reichley's model of level 4. This is the Venkat. Do you know this is they're using the catchment lane surface model. I don't know if it's with GPM or not. I have a feeling that it's not actually. I'll tell you in 10
But
minutes.
It's global, so probably it's not in situ.
Right. It is. It might be GDAS. It might be a blended product. I know that the latency for the soil moisture level 4 is on the order of 7 days. And I think that is because they're waiting. There's a latency in the meteorological forecasting. So for that reason, I'm going to guess that it is not GPM.
Thank you very much.
Thanks for the question. Any other questions? You guys can make me sweat. You can try to ask there's a lot that I don't know.
It is possible, or you recommend to correct the soil moisture images with local data of soils and relieve?
Do you mean to combine ground-based soil moisture observation with a satellite-based soil moisture observation?
No, I see you define a model called Palmer model that takes data from land cover, elevation, and soil properties
Yes.
to make some corrections.
Yeah, so the Palmer model is, if you're not familiar, Palmer model is a relatively simple 2-layer model that it combines soil texture. It uses something called available water content, AWC, and that inherent in that variable is soil texture. So that's what they've done. Yeah, that's right? Yeah, if I remember right. It's been a few years since I did it, but yeah, AWC was used as that, and that's a pretty simple approach, and that's why that was a pretty easy project to do. It's like, oh, we can perhaps improve upon that.
But it would be good to do that, or it will improve the images.
So the reason we used that Palmer soil moisture model is that it requires only 2 variables, temperature and precipitation. So this is driving, this drives your evapotranspiration, and also so there's only 2 observations there, but that's driven by the roughness and the soil type as well. But the reason we use the Palmer soil moisture model, it was a way of demonstrating a value, or a way of getting the surface observation of soil moisture to constrain and update the root zone. So it was a very clear connection between the surface and root zone. But as far as if we should have soil texture, you're saying, can we improve upon the soil texture estimate? Sure. And there's several more types of more complex land surface models that are process-based models that are more accurate, if you will, that require that you can include more accurate estimates of surface temperature and soil type and land cover, land use, and things. And we have examples of that. In fact, the catchment model that was mentioned, tomorrow, I think John Islander is going to be talking, or maybe on Friday, we'll be talking about GLDAS, Global Land Data Assimilation System, on Thursday. Yeah, on Thursday, and also the Land Information System, which is a suite of hydrologic models woven into a system where you can assimilate different types of data.
Thank you.
That was a very long answer to saying yes.
Yes, in Uruguay we have very information of soils, good information of soil, and maybe in a kilometer, square kilometer, we have 5 different soils textures.
Yeah.
So
That's the whole, that's a good point because
it's not homogeneous at all.
no, and when we're doing all this modeling, does it make sense to have the most accurate and the most finite spatial resolution of data? When I'm looking at soil moisture, what's driving soil moisture changes are the meteorological changes are on a spatial order, several orders of magnitude larger than what is driving surface temperature changes and land cover changes. And if you look at a precipitation change, and this is when I look to my friend Venkat and say, Venkat, was that right? And he's always eager to answer. That's what he does.
So I want to just chime in. So your argument about soil texture and soil type is great. But so we're talking about two models here. One is the hydrological model, a simple one like Palmer model or SWAT or whatever. So in that, the soil type and soil texture play a role with respect to the relationship between unsaturated hydraulic conductivity and saturated hydraulic conductivity and the pore structure. So basically the Brooks-Corey or Van Gunington relationships. So just because you have lots of textures doesn't mean you have a lot of those hydraulic properties, as we call it. It doesn't mean that. I mean, unless you have research in a lab and say that clay silty loam over here has this property, and that can be put into any model which John or his group does. Now, the second part is the soil texture also plays a role in soil dielectric modeling, because, you know, the way you get soil moisture is by dielectric constant. And the dielectric constant of the soil is dependent on three factors. One is the solid particle, one is the water, and one is the air. Now, water and air are constant. The solid particle, it has a dielectric constant based on the type of soil. That again, you have to do research to establish those things. Otherwise, knowing soil texture does not get you any extra stuff, either in hydrology or in remote sensing. So, I mean, it's good to know the soil textures, but you have to know the other stuff which goes with it. I hope
That's a good question. In my research, I've always focused on the simpler approaches, because my work has mostly been trying to demonstrate the utility of satellite data for hydrologic applications. And to be honest with you, the Palmer model has fewer knobs to turn. And when I'm designing a data assimilation system, the fewer knobs means it's easier. And I can isolate the value of that. One of my jobs is calling up the NASA headquarters and say, listen, wow, we were able to really demonstrate how we can improve this hydrologic model, or this 2-layer soil moisture model. Now there's much more complex models, and that's also being done. But for my personal research, I've gone the simpler route, because it's I really just like to isolate that value. If that makes sense. But it's a great question. Thank you. Are you guys ready to get to work and have some fun? Harry's excited.
Thank you, John. Clap for John. As John mentioned, we just over the lunch break tried to adapt one of the scripts from Venkat's, Dr. Lakshmi's presentation, because people had some questions about how they can change that code to maybe look at a different.
Got okay.
Just Venkat.
No doctor.
No doctor.
No doctor.
Okay. Call him Venkat. So because we just made those changes just now, it is actually not on the GitHub yet. So I can push it very quickly, and everyone can have more practice doing a Git pull and seeing how we can use this tool as a real-time collaboration, or we can just show the demonstration and they can work through the thing later. So that's does anyone have any preferences?
Well, let's say maybe a show of hands. Oh, yes. Okay, so option one is we just do a demo you don't have the updated GitHub yet, and you watch, and we explain it, or we can, how long would it take to do the push? Okay. Or we have a 10-minute break and we can do it together and do this exercise. Yeah, I say we do a break because what I'd like to see is that each table or each person select a basin of interest from this website. We'll pull this into the script and then we can generate our own soil moisture and time series maps. I think it would be more fun and more useful. That's my vote. Is there any votes for just doing it now? Raise your hand if you want to do it, take a 10-minute break. I think we'll take a break. Okay. 10. Oh, you needed my laptop.